Alkanes are saturated class of hydrocarbons, which means that in this case, a single bond is present between carbon atoms. And we need to remember that actually, saturated compounds are those compounds which only contain a single bond present in them. First of all, we need to understand the general formula of alkanes, and it is CnH2n plus 2. Keep in mind here, N represents the total number of carbon atoms present in alkane. To understand it deeply, let's apply this formula to a few examples. If the number of carbon atoms in alkane is equal to 1, it means that by applying the formula, we will get methane with the formula CH4. And also, you need to keep in mind that methane is the simplest alkane. Now, if we apply this formula when N is equal to 2, we will get C2H6, which is called ethane. Keep in mind that by applying the same formula for any number of carbon atoms, we can find out how many hydrogens will be present in each case. Now let's understand why alkanes are also called paraffins. Here, we need to remember that paraffins is a Latin word, which is actually a combination of two words, and they are parum, meaning little, and affinis, meaning affinity, which tells us that alkanes are actually very less reactive. The main reasons for the less reactivity of alkanes are due to the non-reactivity of the sigma bond present in alkanes. Now let's move towards the nomenclature of alkanes. To understand it deeply, first, we need to learn some important rules. The first and most important rule is that we have to select the longest possible carbon chain, which will give the parent name to the alkanes. To understand the first rule, let's have a look at the following structure. Since the longest possible chain has 5 carbons, we need to select it. Now, if we move towards the second rule, it says that if the parent chain has any branch or substituent present on it, then numbering will start from that side, which gives the least number to the branch attached. To understand it, let's look at the following structure. In this case, since the methyl group is present on the second carbon from the left side, we have to start numbering from left to right, and its name will be 2-methylpentane. Moving towards the third rule, if branches are identical, we should use prefixes such as di, tri, tetra, and so on. But keep in mind if branches present on the parent chain are different, we need to follow alphabetical order, which means that if the parent chain has both methyl and ethyl groups present as branches or substituents, then in this case, since ethyl comes alphabetically first before methyl, we will write ethyl-methyl rather than methyl-ethyl, which follows alphabetical order. Now we should move towards the preparation of alkanes. First, we will discuss the preparation of alkanes from alkenes and alkynes. Keep in mind that alkanes can be prepared from the hydrogenation of unsaturated hydrocarbons, such as alkenes and alkynes. Actually, hydrogenation refers to the addition of hydrogen, and in this case, hydrogenation is done in the presence of catalysts, such as nickel and platinum. If we look at the reaction for the formation of alkanes by hydrogenation of unsaturated hydrocarbons, in this case, ethene will react with 1 mole of hydrogen, which will result in the breaking of the carbon-carbon double bond and will lead to the formation of ethane. Now we should move towards the Wurtz reaction for the preparation of alkanes. We need to understand that this method is used to prepare higher alkanes. In this case, alkyl halides react with sodium in dry ether to form alkanes. If we look at the reaction, in this case, 2 molar concentrations of methyl bromide will react with 2 molar concentrations of sodium to form 1 molar concentration of ethane and 2 molar concentrations of sodium bromide. Keep in mind that we can also prepare alkanes from the decarboxylation of carboxylic acids. In this case, first, we need to understand that actually, decarboxylation means the removal of the carboxyl group, and if we remove the carboxyl group, it will result in the formation of alkane. Keep in mind that this reaction happens when the sodium salt of carboxylic acids reacts with soda lime. If we look at the balanced chemical reaction for the formation of alkanes, in this case, 1 mole of sodium acetate will react with 1 mole of sodium to form 1 molar concentration of methane and sodium carbonate. Now, we should move towards reactions of alkanes, but keep in mind that although alkanes are chemically inert, they can still undergo some reactions such as thermal or catalytic reactions and substitution reactions. In a complete combustion reaction of methane, it will produce carbon dioxide and 2 molar concentrations of water molecules, but if an incomplete combustion reaction takes place, it will result in the formation of carbon monoxide and water molecules. Now, if we move towards the catalytic oxidation of methane, it can change into formaldehyde and formic acid. You need to keep in mind that catalytic oxidation means the addition of oxygen in the presence of a suitable catalyst. During this reaction, in the first step, methane will react with a water molecule to form methanol. Next, in the second step, methanol will be converted into formaldehyde. And finally, the oxidation of formaldehyde will change it into formic acid. Now let's move towards a very important reaction of alkanes, which is called the halogenation of alkanes. This reaction takes place in the presence of sunlight, and it follows a free radical mechanism. Keep in mind that a free radical refers to a highly reactive species with an unpaired electron. Actually, the free radical mechanism takes place in 3 steps, which are initiation, propagation, and termination. In the first step, during initiation, the formation of radicals takes place. During the second step, propagation takes place. Remember that propagation means the growth of free radicals. In this step, radicals will keep on growing during several reactions and will result in the formation of many valuable products. In the last step, 2 radicals will react with each other to form a stable product. Here, we need to understand that termination refers to the ending or termination of radicals. If we look at the mechanism of the halogenation reaction, in this case, during the initiation process, a chlorine molecule, which means Cl2, will break down into 2 chlorine radicals. In the second step, which is called propagation, these chlorine radicals produced in the first step will react with methane to produce many valuable products by the successive replacement of hydrogen atoms with halogen. And after that, finally, in the third step, which is called termination, here, a methyl radical will react with a chlorine radical to produce methyl chloride. As we can see that in this case, in the products, no radical is formed. So from here, we can say that during the halogenation process, in the third step, radicals are terminated. Now let's move towards isomerism phenomenon in alkanes. Actually, isomerism in alkanes occurs when compounds have the same molecular formula, but different structures. This means they contain the same number of carbon and hydrogen atoms, but their atoms are arranged in different ways. This type of isomerism in alkanes is called structural isomerism, specifically chain isomerism. It happens when the arrangement of carbon atoms in the chain changes, leading to different physical and chemical properties. Now let's understand chain isomerism in alkanes. Alkanes can exist as straight-chain or branched-chain isomers. Straight-chain isomers have all carbon atoms connected in a continuous line without any branches. And branched-chain isomers have at least one carbon atom attached to the main chain as a side group, forming a branch. Even though these isomers have the same molecular formula, their properties, such as boiling points and densities, can be different because of their structural differences. To understand it deeply, let's take the example for the possible isomers of butane. Remember that butane is an example of an alkane that shows chain isomerism. It has 2 isomers and they are straight chain and branched chain. In straight chain structure, all 4 carbon atoms are connected in a straight line. This isomer has a higher boiling point than its branched counterpart because its molecules can pack closely together, leading to stronger intermolecular forces. But if we look at the branched structure, 3 carbon atoms form the main chain, and the 4th carbon is attached as a branch to the 2nd carbon. Because of its branched structure, isobutane has a lower boiling point than N-butane since its molecules cannot pack as tightly as straight-chain molecules. One important point we need to remember that as the number of carbon atoms in alkanes increases, the number of possible isomers also increases. This is because there are more ways to arrange the carbon atoms in different chains. For example, pentane has 3 isomers, hexane has 5 isomers, and heptane has 9 isomers. This proves that the number of possible isomers increases rapidly with more carbon atoms, making it more difficult to name and differentiate them. Now, let's understand physical properties of alkanes. We need to understand that alkanes have specific physical properties that depend on their molecular size and structure. These properties include boiling points, melting points, and solubility. Since alkanes are non-polar molecules, their behavior is mainly influenced by weak London dispersion forces, which are temporary attractions between molecules. First, let's have a look at melting and boiling point. The boiling and melting points of alkanes increase as the number of carbon atoms increases. This happens because larger alkanes have more electrons and a greater surface area, leading to stronger London dispersion forces between molecules. More energy is needed to break these forces, which results in higher boiling and melting points. For example, methane is a gas at room temperature, but octane is a liquid because it has stronger intermolecular forces. Keep in mind that the structure of an alkane also affects its boiling point. Branched-chain alkanes have lower boiling points than straight-chain alkanes of the same molecular formula. This is because branched molecules are more compact and have less surface area for intermolecular forces to act, making it easier for them to evaporate. For example, N-pentane has a higher boiling point than its branched isomer isopentane. Now let's discuss solubility of alkanes. Alkanes are insoluble in water because they are non-polar, while water is a polar solvent. The principle like dissolves like explains why non-polar substances do not mix with polar substances. Water molecules attract each other strongly through hydrogen bonding, and since alkanes cannot form these bonds, they do not dissolve in water. However, alkanes are soluble in nonpolar solvents like benzene, ether, and chloroform. This is because nonpolar solvents have similar weak intermolecular forces, allowing alkanes to dissolve easily. Now let's discuss some important use of alkanes. Alkanes like methane, propane, and butane are used as fuels in homes, industries, and vehicles. Methane is used in natural gas for cooking and heating. Higher alkanes, such as paraffin wax, are used in making candles, polishes, and waterproof coatings. They also serve as lubricants in machinery and engines to reduce friction. Alkanes like hexane and heptane are used as solvents in industries for extracting oils, cleaning, and dissolving nonpolar substances. They are also used in paints and coatings. Alkanes are also the main components of crude oil and are refined into different fuels like petrol, diesel, and kerosene. Alkanes also serve as raw materials for making various chemicals, including alcohols, plastics, and detergents. They undergo chemical reactions like halogenation to produce useful compounds for different industries.